Happy April Fool's Day, everyone. It's April 1st. Mr. Dolowitz here. So I'm doing our weekly lesson different this week than I did last week. And the aim moving forward for the rest of the semester is to record videos like this. So, excuse me. More about that later in class, but I want to take this time right now to just, oh my gosh, hiccups. Just to go through the lesson. So this is for lesson 11.6, which is titled Events Involving Not and Or, and then another topic called Odds. So you should have access to this document in your email as well as the weekly outline. You can find that there. Okay. And off we go. So please have this document ready and following along. So I want us to consider a standard 52 card deck. One card is going to be randomly dealt. What's the probability that it's the ace of spades? You don't need me for this. We've talked about this last week. The probability that it's the ace of spades, there's one of those in the entire deck of 52. What's the probability that the card, not car, sorry for the typo there, is not the ace of spades? Well, yeah, the answer's already there, but does that make sense to you? So if one of them is the ace of spades, that means everything else is not it. So that means there are 51 out of 52 cards that are not the ace of spades, and therefore the probability is 51 out of 52. Now, this is building up to something that's almost obvious, but I hate using that word. I'm a math person. I've done this for many years now. Not that many, but whatever. But it's kind of obvious if you think, what's the probability of something happening or combined with the probability of that not happening? So, for instance, think about, I say tomorrow, you're going to win the lottery. There's probably some probability associated with that. Very small. You're not going to win the lottery. But if I find the probability, whatever it is, with the probability that you're not going to win it, one of those two things is going to happen. Either you're going to win it or you're not. And therefore, those probabilities, since one or the other is definitely going to happen, the probability, or you're going to win the lottery or you're not, well, their probabilities, one of those things are going to happen. So the two of them combined have to add up to 100%. Either you're going to win or you're not, but we're not looking at them individually. We're saying combined, they have to, one of those things is going to happen. Either you're going to win or not. So 100%, you're either going to win or not. And that's going back to this lesson. What's the probability of the sums of either getting the ace of spades or not the ace of spades? 1. Same idea. Either the next card is the ace of spades or it's not. But the probability of something or not something is always going to be 1. And that's our first rule, if you will, for a section 11.6. The probability of an event plus the probability of not that event is equal to 1. And I have that spelled out right there. Symbolically, in math symbols, we write P of E, which stands for event, plus P of E prime, which looks like an accent mark, equals 1. All right, so that's the symbols in mathematics. And E accent mark, properly read as E prime, is called the complement of E. All right, but the main point there is the E apostrophe, or yeah, I think that's the word I was saying. I can't. E apostrophe. Yeah, I don't know what I was just saying. Accent mark, same idea. E apostrophe is properly read as E prime, and it means the complement of E, which means not E. That was a mouthful. All right. So back to the slide here. Where are we at? What I'm doing now is saying we can solve the equation that is written in blue at the top right corner by for P of E by just subtracting P of E prime from both sides. And basically, all this is mathematically is saying that the probability event is 1 minus the probability of its complement. Right? And for whatever reason, our textbook author creates the same statement in terms of P of E prime, but don't get bogged down there. The real main point here is the probability of event is equal to 1 minus its complement. That's all that slide was showing there. So now we're going to look at, suppose two events occur at the same time. Let me back up here for a moment. If it is impossible, there I was missing that key word there. If it is impossible for two events to occur at the same time, we say in mathematics that those events are mutually exclusive. So one example I can think of right now is I'm going to pick a card out of a deck. Actually, that's one that's already in the notes. I'm going to flip a coin, and I will get, I don't know. I'll come back to you in a second. Let's just stick with the lesson here. Mutually exclusive event. So two events going to happen, but they can't happen at the same time. I'm just bogged down with the example I wrote up in class. So suppose we have the event of selecting a jack. Suppose we have the event of selecting a queen. If one card is randomly dealt from a 52 card deck, then the probability of getting a jack or a queen, since they can't happen together, it is impossible to have a card that is both a jack and a queen. What mutually exclusive means, there's a good example. I'm going to pick a card out of the deck. What's the probability it's a jack or a queen? Well, it can't be. There's no such card as a jack queen. There's no jack and queen at the same time. So those are mutually exclusive events. More on that as we get through. Okay. But the probability for two mutually exclusive events separated by the word or, P of A or B is equal to P of A plus P of B. A lot of antics and wording, and I'm getting tripped up myself. So let's just look right at an example. So suppose we roll a standard die. What's the probability of rolling a 5 or an even number? We're going to look at this two ways. So what should we call event A? Rolling a 5. What B? An even number. Boom, boom. We need to complete a Venn diagram with all the outcomes, including event A and event B and everything else in the universe. If I roll a die, I can get a 1. That's not in set A or B. Get a 2, which is an even, a 3, which is not in set A or B, a 4, a 5, and a 6. So that's all the outcomes of rolling a single die, and A being the number 5, B being an even. But if we look at this intersection, there are no shared outcomes. So you can think of a Venn diagram as a way to say, hey, it's a mutually exclusive event is two events that have nothing in their intersection. And that's all I wanted to drive there. Two events are mutually exclusive. And you don't necessarily have to draw a Venn diagram, but it might be helpful to do it. But if you can visualize it in your brain, say, if I were to do this Venn diagram, nothing would be an intersection, then you have two events that are mutually exclusive. And then I'm using the diagram to find the probability. Let me back up there for a moment. I will get better at balancing two screens at once. But the last question says, use the Venn diagram to calculate the probability. Well, the probability of A plus the probability of B. Oops, I didn't want to do that. What I really wanted to show was using the Venn diagram. So if you were watching, pay no attention to here. I'm going to wind up erasing it. But looking at the Venn diagram, there are 1, 2, 3, 4 favorable outcomes that I highlighted in green or checked with a green out of a total of 6. So by the diagram, 4 out of 6 is the probability of rolling a 5 or an even, which simplifies to 2/3. So the second way we're going to do this is using the formula. The probability of, well, first explain why the event A and B are mutually exclusive. It's impossible to get an even 5. Now, how can we calculate the probability? The probability of getting a 5 is 1 out of 6. The probability of getting an even is 3 out of 6. And since they're mutually exclusive, we just add those probabilities together and get 2/3. And it's nice to see that the mathematics holds, meaning you can get the same answer in 2 different ways, one very visually, one by the formula. This last part here is an open question, and I would suggest that we're going to read this question, and then you're going to take a moment, 2 to 3 minutes or 5 minutes, and try to answer this yourself. Don't proceed with the video. Don't hit play anymore. Pause the video after we read this prompt and give it some thought. Suppose rolling a standard die. Suppose you're rolling a standard die. What is the probability of rolling an even number and a number greater than 3? So some student argues that if event A is rolling an even and if event B is rolling a number greater than 3, then the probability of A or B is equal to P of A plus P of B. That's what we're doing. And now let's go back. So A is rolling an even. Well, that happens for 3 out of 6. And the probability of a number greater than 3, well, that's rolling a 4, 5, or 6. Again, 3 out of 6. So by the definition we were using above, P of A plus P of B, 3, 6 plus 3, 6 equals 6, 6, or a whole. So what would you think? Is this a reasonable result? Give it some thought. Is it reasonable? Yeah. It's reasonable because no, it's not reasonable. Why not? Well, the bonus gives a hint. It's not reasonable because I'm asking you to actually calculate the probability. Why is there a bonus question that's asking to calculate the probability if it's written right there as 1? So something's wrong here. That's my last little hint here. What is unreasonable about this? So that's it. You don't have to try to say, well, I know how to get, I'm going to figure out the probability. But what right now can you say to this student and just say, listen, you don't have a reasonable answer. I might not be able to get the answer, but your answer is not reasonable. Why? Then the extension is, can you figure out how to calculate the probability right now? So I encourage you to do that, but we're going to move forward. So if you haven't done it, spoiler alert, here we go. On the back side of the sheet, let's consider that last example. Clearly, the result of 1 is not reasonable. A probability of 1 means we're definitely going to get something to happen. However, it is very possible to roll the number 1, which is either or neither even or greater than 3. And the fault in the logic here was these events are not mutually exclusive. So going back to the question a moment ago, it's not reasonable, I would argue to that student, you're saying the probability is 1, which means you're either going to get a 5 or a number greater than 4. No, like for instance, what if you got a 1? I'm sorry, what was it? I actually forgot what the question was. Oh yeah, it is very possible to roll a number 1, which is neither even or greater than 3, right? So 1 is not even, it's not greater than 3. So 1 is a possibility that can happen. But you're saying 100% we're going to get an even or a number greater than 3. So there's the faulty logic. But let's continue on. So we'll look at a Venn diagram to see the sample space like we did before. I know I made a mistake when I was writing this up, so I know I'm going to end up erasing it for a moment here because I couldn't fit all the numbers. But A is that we roll an even. B is the event we roll something greater than 3. I think I just said 4, greater than 3. So let's do this nice and clean. I can get a 1, a 2, a 3, a 4, a 5, or a 6. Both 4 and 6 are numbers greater than 3 and even, so they live in the intersection of A and B. And therefore, the event are not mutually exclusive. So a big question here, another big question to ponder and think about, you mathematicians. What is the probability of events that are not mutually exclusive joined by or? And I'm about to write it. So give you another moment if you want to think about what that result is. What is the formula? The hint is we just have to modify what we already have working for us. There's an additional term. That's my hint. I'm about to write P of A plus P of B, but there's something we need to do. So think about it. And now the reveal. We're going to write P of A plus P of B minus P of A and B. We have to subtract the intersection. Why? So I use some highlighting here. There's the probability of A, highlighted in yellow. There's the probability of B. There's the outcomes you can get. And in the middle, 4 and 6 right there was counted in both of those. We don't want to count 4 or 6. 4 or 6 is over counted, so we need to subtract it. 4 and 6 was counted in both sets, A and B. I don't want to count those elements twice. I just want to count them once. I want to go through and say, all right, 2, 4, 6, and 5. There are 4 possible things. But if I just count A, I count 2, 4, 6. If I count B, I count 4, 5, 6, 4, and 6 twice. We need to subtract the intersection once. Right? Let me back up here. So suppose we draw a card from a standard 52 card deck. Find the probability that it is a 7 or a red. Well, these are not mutually exclusive events. So I write P of 7 plus P of red minus P of 7 and red. What's the probability of a 7? Well, there are 4 of them out of 52. What is the probability of a red? There are 26 out of 52, or half the cards. And how many are 7 and reds? Well, there are 2. There's the 7 of diamonds and the 7 of hearts. So we subtract 2 out of 52. We nicely have a bunch of common denominators. So 4 plus 26 minus 2 makes 28, which at the end of the day, that entire fraction simplifies to 7/13. Find the probability that the card is a heart or a pitcher. Well, those are not mutually exclusive events. You can get a pitcher card that's a heart. So we find the probability of heart plus the probability of picture minus the probability of the heart picture cards. Probability of heart is 13 out of 26. The probability of a pitcher is 12 out of 50. Why did I say 30? Probability of a heart is 13 out of 52. Probability of a pitcher is 12 out of 52. And the probability of their intersection is 3 out of 52. So kind of just zoom in there, talk quick, pay no attention to what I'm listening to, more attention to what I have written there. That is correct. Yep. Double checking it. Probability of heart, probability of a picture, probability of heart and pitcher we subtract. So 13 and 12 make 25. Take away 3 is 22 out of 52, which simplifies to 11 out of 26. Wonderful. All right. So there's how you calculate probabilities involving the word or, and the events are not mutually exclusive. So a few things so far before kind of wrapping up the lesson. There's just a tiny bit more, but complement, keep that working. What is a complement? It's not the event. So tomorrow is going to be sunny. The complement is not going to be sunny. All right. What's true about complements? Well, the probability of an event plus the probability of the event's complement always equals 1. And then you can manipulate that to say, in other words, the probability of an event is 1 minus its complement. Right. So we're saying the same things in multiple manners. The probability of 2 mutually exclusive events. Mutually exclusive are events that cannot happen simultaneously, like drawing a jack and a queen from out of one card. Not possible. The probability of A or B, if A and B are mutually exclusive, exclusive is the probability of A plus the probability of B. But what we've just seen now is what's the probability of getting a 7 or a red card? Well, I could get a card that is both 7 and red. So therefore I have an event or two events that can happen simultaneously. Therefore, they're not mutually exclusive. You modify the formula to say P of A plus P of B minus their intersection P of A and B. That's it. So one more example with that. We'll talk about odds, and we're done for this lesson. A student selected a random group of 200 students in which 135 take math, 85 English, and 65 take both math and English. What's the probability that the selected student takes math or English? So what I've done there is I symbolically translated the word into math symbols. The probability of math or English. Well, we're told right in the problem that there are students that are in both. So we'll calculate the probability of math plus the probability of English and subtract their intersection. Just reading the questions values. You get these following numbers, which today I'm not doing a good job reading numbers, so I'm just going to monitor my work. All looks good. Looking at the arithmetic now, add the numerators or combine them, add and subtract. You end up with 155 over 200, which simplifies to 31 over 40. Okay, we're now at the last part of the lesson, which is defining odds. So here's a video, utu.be/p1nagtuix4s. If you don't have the hyperlink, you can type it in. It is, or you could just Google search odds versus probability. It was it's I think the first or second video, it's 1 minute and like 30 seconds. So in gambling, odds has or I just say gambling, but mathematics, odds has a very specific definition, and it's not equivalent to probability. They're not the same definition. So informally, most people, I would say, go walking down the street and say, hey, the probability of rain is da da da, but the person next to them will go home and say, hey, I heard the odds of rain tomorrow are, well, yeah, informally, we don't pay attention to that. But that's how casinos and lotteries lie. They purposely make things tricky, just like Wall Street, right? They come up with terms and ways to confuse us, so we don't understand the numbers. They purposely confuse us, right? But that's my point. Be very careful, at least in this course, at least when you're doing your homework, at least if you ever make it a Jeopardy. Probability and odds are different. Our book just has a one-sentence blurb and says, here's the definition of odds. Doesn't really go into it. So I don't want to spend any more time than I really need to, but this 1.5 minute video does a nice job of kind of just describing the difference. And now we'll do what our definitions of it. So if you want to take and convert probabilities to odds, well, you have to, there's two common phrases. The first one is odds in favor of an event, and that's found by, and I'm sorry, the other one is odds against an event. So if we look at odds in favor, what you're doing is creating a ratio. Okay, so that's what I'm looking at. And the ratio is the probability of the event, and the denominator is the probability of its complement. And the odds against, I don't know why it says odds in favor again. There's a typo there. So this should say odds against. I obviously copied and pasted it, but did not change that. So my apologies. Right here, right there, should not say odds in favor. It should say odds against, okay? It's literally the inversion of odds in favor. We have the probability of the complement of the event, and in the denominator, we have the probability of the event. That's it. So you're still calculating probabilities, but you're actually calculating two probabilities, creating a ratio, and depending on the wording, if it's odds in favor, you're creating the ratio that's highlighted in yellow. If it's odds against, you're creating the ratio that's highlighted in red. And if you need to convert odds back to a probability, then the formula to do that is, let me read this. If the odds in favor of an E are A to B, so if you have odds A and B, or A to B, the probability is A divided by the sum A plus B. Right. So again, very abstract wording and letters, but the idea is really simple once we apply it. So my last examples here. One card is selected from a deck of cards. Find the probability. Find the odds. Ooh, even I just caught myself. Find the odds in favor. I immediately write the formula. What's the now probability of drawing a picture card? 12 out of 52. What's the complement? Well, 40 out of 52. There are 40 cards that are not picture cards. Basic arithmetic here, we're allowed to cross out those 52s. So we're looking at 12 divided by 40, which simplifies to 3/10. What are the odds against drawing a jack? Against means we're going to calculate the probability of the complement and divide that by the probability of the actual event. So I start by calculating the probability of the event. Drawing a red jack, there's 2 out of 52, which means there are 50 out of 52 that are not. The arithmetic says we can cross out the 52s. You get 50 over 2, which is 25 over 1. And there are multiple ways to write odds. You can write it as a fraction. You can write it using the word 2, or you can write it using semicolons. All are acceptable. 38 plays are attributed to Shakespeare. 18 are comedies, 10 are tragedies, 10 are histories. Find the odds in favor of selecting a tragedy or a history. Well, there's the word or, but these two events are mutually exclusive. You can't get a tragedy or a history. Shakespeare's play are classified as one or the other, not both. So the probability of getting a tragedy or history is 10 out of 38 plus 10 out of 38, which makes 20 out of 38. Therefore, the complement is 18 out of 38. And then we cross out the 38s. Arithmetic allows us to do that. We're left with 20 out of 18, which simplifies to 10 out of 9. What's the odds against selecting a comedy or history? Again, we have comedy and a history are mutually exclusive events, so we can calculate the probability of comedy plus the probability of history, which makes 20 out of 38. Therefore, that means there are 10 which are not. Therefore, 10 out of 38 is a complement. Cross out your 38s. You're left with 10 over 28, which simplifies to 5 over 14. And finally, we're going to convert odds to probability. If you're given odds A is 3 to B, which is 7, calculate the probability. The last formula says you take A and divide it by the sum of A plus B, and you're left with 3 over 10. So I know I have a little work to do with recording these videos in terms of timing and speed. And honestly, I've been lacking in sleep myself, so I know I'm a little bit off on that today anyways. So I apologize, but I really want to do these recorded videos for a lot of different reasons. So be prepared for another video tomorrow on the next section, and I'll see you in class. Take care. Stay safe and wash your hands.